Okay, the next thing we're going to talk about is the formation of dolomite. We've already said that dolomite is primarily a replacement of limestone, but we want to talk a little bit more about how that happens and what some of the problems have been with trying to form dolomite in the laboratory. So remember, the formula for dolomite is CaMgCO3 2, which means that basically we're going to replace one calcium ion with a magnesium ion. So we've got to basically shove Mg2 plus into the same place as Ca2 plus in the limestone. And we end up with a different mineral. We've already said that it doesn't take the alizarin red staining. Commonly you'll see that it occurs as crystals, euhedral in shape, in rocks where the dolomite is a replacement or secondary. We also talk about dolomite as being fabric selective or fabric destructive. By fabric selective, we just mean that basically we replace every ion of calcite with an ion of magnesium, and we preserve the general sedimentary structures we see. Fabric destructive means that as the dolomite grows in size, it destroys the fabric of the rock itself, so it's almost impossible to see what was the original depositional shape, or what were the minerals, or what were the, not the minerals, but the grains within the limestone to begin with. So those are just some of the things we think of. You also may have seen in the book something called the dolomite problem. And the dolomite problem is basically the fact that for over 100 years, people in laboratories would take normal marine waters, which we can test and show that are highly oversaturated with respect to dolomite, and yet by no combination of things that we did to the water, either raising the temperature or increasing the pressure, could we make dolomite, except until you got to things that were not normal on the surface of the earth. So we could take seawater and we could almost boil it, get it up to 99 degrees Celsius, and then you could start to make dolomite. But below that, you couldn't make dolomite, and it would take, you just couldn't make it. We had people who actually ran experiments for over 20 years in their labs and couldn't make a speck of dolomite. Okay, so that was the dolomite problem, was that we couldn't, at naturally occurring conditions in the lab, reproduce dolomite, even though we had the same fluids that we know make dolomite. So that was a dolomite problem. We'll come back to how we sort of think we may have gotten towards solving that. But we're also going to talk about mechanisms to make dolomite. And if you remember, if I'm going to replace magnesium, if I'm going to shove magnesium into the calcite lattice, what I've got to do is I've got to have, to make dolomite, I've got to have two things that have to occur. One is I have to basically have some pump. So I have to have a way to push many volumes of marine fluids or marine waters through the rock. And what that does is it allows many volumes of magnesium to be able to react with the rock so that it's easier to make dolomite. So we need to have some sort of a pump, and we'll talk about what that might be. And the other thing we need to do is we need to increase the magnesium to calcium ratio. And the best ways to do that are through evaporation. So if in my evaporation I basically get rid of seawater, then I start to have more magnesium and calcite in the water. And if I've gotten any sort of precipitation of skeletal grains, they're using up all the calcium, so then I've got more magnesium left over. The other way we can do it is through concentration. And one of the best ways to concentrate magnesium is through burial. The burial fluids that are deep in the ground, they have lots and lots of salts in them. One of the salts they have quite a bit of is magnesium, and so that raises the magnesium-calcium ratio. Okay, so we want to make dolomite. And I'm just going to give you one example that your book talks about at least 3, and there's many more ways to make dolomite. The one we're going to talk about is called seepage reflux. And we know this works. We've seen it in the rock record. If this is my carbonate platform, and there's my reef is doing what it's supposed to do. It's basically separating the lagoon from the open ocean. Well, back here in this lagoon, if you're in an arid climate, what's going to happen to the waters back here behind the reef? They're going to start to heat up, and then you're going to get evaporation. If you start to get evaporation, then the water becomes full of all these excess minerals. So this actually becomes a brine. Okay, so the waters in here become a brine. Their density is much higher. And so commonly what happens is they will start to move through the rock, eventually coming back out and interacting with oceanic waters. But as those brines move through the rock, they start to produce dolomite. And so you'll get abundant dolomite that will form in here. And so commonly what happens is you'll see a zone beneath the lagoon where the waters are migrating out back to the open ocean, and that's where the dolomite is occurring. Okay, so we've seen this in the rock record. We've seen this through cores where people have drilled through carbonate platforms, and you can see this sort of movement of dolomite from near the lagoon down into or out towards the open ocean. So this is just one way of doing it. This allows us to have our pump because now we've got lots of volumes of water. This basically, every time the tide rises, it brings us more water. It evaporates and we make this brine. And we also, because of the evaporation, we get this concentration of magnesium, which then can be pumped down through these rocks and make it easy to turn this into dolomite. Okay, so that's just one. There's many other ways to do it, but that's just one of the common ways that we see in the rock record that this works. The other way that your book talks a little bit about, and it's a little bit different, but it basically, we think, has helped us solve some of the dolomite problem. This is sea level up here. And the reason we think this is because we've seen this now in lagoons down in Brazil. In the bottoms of these lagoons, this water becomes anoxic. Okay, so right down here, right at the sediment water interface, this becomes anoxic. And as it becomes anoxic, sulfate reduction starts to occur. So we've got SO4, 4-, and we reduce this. And as we reduce this, what happens is we start to have lots of magnesium 2+ that's available now to react to make dolomite. Previously, before the sulfate reduction goes on, the magnesium would also bind with the oxygen. It's very, very reactive. But because of this sulfate reduction, it allows there to be lots of Mg in the water. So as this water comes down and interacts with this sediment water interface, then we can start to make little tiny crystals of, not of dolomite, but of proto-dolomite. So we make this proto-dolomite, which is basically dolomite that is not stoichiometric. It doesn't have 50% magnesium yet, but it has some magnesium. It's starting to become dolomite, and it makes this proto-dolomite. And as the rock sits here, as the sediment sits here and we have more sulfate reduction and we start to fill up this lagoon, what happens then is the proto-dolomite turns into ordered, what we would call, what the book refers to as stoichiometric dolomite. Now, the beauty of this is this process is going on the seafloor, present day, in these lagoons. So we think what this has helped us do is to get over the dolomite problem. In many cases, it can be shown that if you start to initiate dolomite in this kind of an environment, you can imagine if we started to have evaporation, we started to push more magnesium, then we could get more ordering of these crystals. And so it's now thought that one of the ways to get over the dolomite problem, and it's been shown in the laboratory, is you take seawater back, you let microorganisms act to do any sort of sulfate reduction, then you can start to have dolomite forming, even out of normal marine waters at normal temperatures. So we think we're on our way to overcoming the dolomite problem, but that was one thing that was a problem in the past. So we'll move on and we'll talk more about skeletal grains, and then we'll talk about depositional environments.